So here's problem 41 from section 4.1. So we're going to look at this. We are going to try to find the local extreme values and by first identifying the critical points. Right, Julie? Right, Julie? Right. Okay.
Right.
All right. So let's remind ourselves, what are critical points? Critical points are where the derivative is either 0 or undefined. Right? So let's start by talking about what does the derivative look like. And the derivative of a piecewise function is also piecewise. The derivative of this is going to be -2 minus 2, and that's going to be when x is less than 1.
Why does that change?
From less than or equal to less than?
Mm-hmm.
Because I want to find out whether it's going to be differentiable at 1.
Okay.
And I'm going to do that in a second. So right now I know, for at least for all of these values, this is going to be okay. And then I'm going to check x equal 1 in a second. All right? When x is greater than 1, we get 2x plus 6. And now my question is, the derivative what is the limit of the derivative as I get closer and closer to 1 from the negative side? As I get closer and closer to 1 on the negative side, this looks like it's going to be -4. As I get closer and closer to 1, this is going to end up being 1. -2 minus 2. This ends up being -4. What about the limit as x approaches 1 from the positive side of our derivative? Looks like it's +4. So my conclusion is that the derivative at 1 doesn't exist. The two-sided don't agree. The derivative at 1 doesn't exist. Hey, if the derivative doesn't exist, know what that means? No, you don't know what that means. It means that x equals 1 must be a critical number, or a critical point, or the location of a critical point, I should say.
Are usually the domains that they give you in piecewise functions a critical point? Is it seeming that way? Like the ones right there, like we did another one in our
It is a very likely occurrence. It's not guaranteed, but it's a likely occurrence that there's a
Wait,
critical.
Mr. Fader, to get the limit as x approaches 1 from both sides, you just plug in -1 and 1?
Well, I plug in 1 here to get for the negative side, because this is the negative side, and then this is the positive side. So I'm going to plug in 1 to this expression. So 1 times -2 is -2 plus 6 is 4. So that's where I got that 4. All right? So there's a critical point at 4. Are there any other places where there are critical points? Well, are there any other places where the derivative is equal to 0? What kind of value could make this expression equal to 0? -1?
Yeah.
If I plug -1 in here, I get 2 minus 2, which is 0. And -1 is less than 1. So I'm going to say x equals -1 is also a critical point. All right? All right? And then lastly, are there any values in here that would make the derivative equal to 0? I would guess that 3.
3.
Yeah. So here are the locations, or at least the x components, of the critical points. All right? All right. Now, when I look at dy dx on a number line, the value -1, the value 1, and the value 3 are locations where the derivative can change sign. The critical points are places where the derivative can change from positive or negative to positive. When we are in this particular part of the number line, what kind of derivatives do I get out? If I put -10 in here, if I put -20 in here, well, I get -20 times -2 is positive 40 minus 2. I say we get positive values out. Right? How about in this interval? How about at 0? 0, I'm going to be less than 1. I'm going to get a negative value. Right? And how about between 1 and 3? How about if I put 2 in? If I put 2 in, I'm going to be, that's greater than 1. Be positive. Right? And then lastly, if I put really big positive numbers in,
It'll be positive. Negative.
negative. Because like 10. 10 times negative 2 is negative 20 plus 6, negative 14.
Do they always alternate?
Don't always, but they often do. All right, so what does this mean? If I kind of sketch in my head, I have a function that's increasing until I get to negative 1. I have a function that's decreasing until I get to positive 1. I have a function that's increasing until I get to 3. And I have a function that's decreasing after 3. Now, I don't know if that function actually looks like that, but it has that increasing, decreasing. The only thing I have to worry, is this function actually even continuous? Can I look here, can I ask the question, is it continuous everywhere? Oh, it's continuous at 1 is really the only question,
Yeah.
place where it might be not continuous. If I put 1 in here, what do I get? Oh, let me be more specific. What is the limit as x approaches 1 of the x approaches 1 from the negative side of y? Negative 1 minus 2 is negative 3 plus 4 is 3. Or sorry, try that again. 1. I think, try that one more time. 1 squared is 1 times negative 1. Negative 1 minus 2 is negative 3 plus 4 is 1. What about here to the other side? This is time. SY, sorry. SR, this two, okay, SYRACUSE.
Is that 3, Julie?
No, fuse. SY, I'm looking at SYRACUSE. Too early in the morning. All right, bye. What'd you get?
Isn't that 3?
Is it 3?
We'll plug in 1 for this.
Okay, so 1, negative 1, plus 6 is
It's 1 plus
5. 5 minus 4 is 1.
With negatives.
Okay.
They
Okay,
agree?
so they agree, so they are
Yes.
continuous. So when I got here at 1, those two graphs do connect. All right? So what do we know? What do we think is going on there?
Oh, I remember that from last year.
What do we think is going on here? We had an increasing function and a decreasing function. I say at x equal negative 1, we have a local max. I say at x equal 1, we have a local min. I say at x equal 3, we have a local max. By the way, the local min is equal to, as we just calculated, 1. And if we plug negative 1 into our functions here, we could find out what that local max is. Negative 1 squared is 1, negative 1 plus 2. Negative 1 plus 2 is 1 plus another 4. That local max is 5. And then when I plug 3 into here, I get what? 9, negative 9, 3, 18. Negative 9 and 18 is positive 9. Positive 9 plus 4 is, minus 4 is 5. So that's number 41.
Okay.
Yeah.
And there are no absolutes.
Well, what do you think?
I mean, absolute minimum.
The question actually only asks for locals.
Oh, no, it's not.
Oh.
Oh.
Is that right? 41? Identify the critical points and determine the local extreme values. It only asks for locals, but what do we think? I think these maxes are absolute. We got up to 5, we came down. We got up to 5, we came down.
But why would 3 also be an absolute maximum?
Because they're both 5.
No, the 3 is the location of it. Absolute,
Oh, because they're both 5. It's just
Right.
in your graph 3.
I'd say the absolute maximum is 5, and there's no absolute minimum. Because these guys are going down, and they're going to continue to go down.
Sounds great.
Okay? All right, so that's 41.
Okay, so when we were doing our homework yesterday, we didn't really know how to get the other, like, critical point. Like, we could get 2 of them, but then we didn't know how to get
wait.
another.
I'm going to leave it's going to stay up there. All I want to do is stop the recording, all right?